Assalamu alaikum. We are discussing molecular spectroscopy for semester 8 physical chemistry, and the topic is rule of mutual exclusion. This rule was proposed by Dr. K.G. Srinivasa Murthy, and this law or this rule gives a relationship between molecular vibrations and molecular symmetry, and it states that this rule can be stated as in a centrosymmetric molecule none of the vibrations will be both IR active and Raman active. In a centrosymmetric molecule, none of the vibrations will be both IR active and Raman active. That is, it means that if a vibration is IR active, then it will be Raman inactive, and vice versa. In a centrosymmetric molecule, none of the vibrations will be both IR active and Raman active. It means that if a vibration is infrared active, then it will be Raman inactive and vice versa. Now, to expand and explain the rule, we take two examples. We take the example of carbon dioxide and we take the example of water. Carbon dioxide is centrosymmetric while water is not centrosymmetric. It has no center of symmetry. First of all, we take first example. We take the example of carbon dioxide. We had already discussed that for a molecule or a vibration, a molecule to be IR active, there must be a change in its dipole moment. If there is any change in dipole moment or polarity of molecule during a vibration, then that vibration will be IR active. For Raman active molecules, the gross selection rule was that they must have a change in polarizability. Now we come to the example of carbon dioxide. Carbon dioxide is a triatomic linear molecule. The total degrees of freedom are 3n, where n is atomicity of the molecule, are 3 into 3, 9. Out of these 9 degrees of freedom, translational degrees of freedom are 3, rotational degrees of freedom are 2. Hence, the remaining degrees of freedom will be the vibrational degrees of freedom. So, the vibrational degrees of freedom will be, vibrational degrees of freedom are 3n minus 3 minus 2, or 3n minus 5, or 3 into 3 minus 5 is equal to 4. Thus, carbon dioxide has 4 modes of vibration, and these modes can be represented as follows. We write down the modes of vibration, normal modes of vibration for carbon dioxide. These 4 modes of vibrations are, the first mode is called the symmetric stretching, in which both the bonds expand or compress simultaneously. Let us suppose it is the equilibrium position of carbon dioxide and the bonds are expanding or the bonds may compress. We had already discussed that the polarizability ellipsoid is represented by this figure. It is the polarizability ellipsoid. As the bond length increases, the polarizability also increase, and as we move towards left side towards expansion, the polarizability increases, hence the polarizability ellipsoid will become smaller in size. And on the opposite side, when we move towards compression of bonds, then the polarizability decreases and the polarizability ellipsoid increase. As alpha, our polarizability changes as a result of this stretching, therefore this stretching will be Raman active. This vibration will be Raman active vibration. Now we consider what happens to the dipole moment of the molecule. Now, on both the extremes, as the bond expands or the bond compresses, there is no change in dipole moment, because the increase or decrease on both sides cancel out each other. There is no change in dipole moment. Here we also have no change in dipole moment. Polarity does not change. That is why this vibration will be infrared inactive. So according to rule of mutual exclusion, this vibration is Raman active, but it is IR inactive. Now we consider the second vibration, which is the asymmetric stretching, in which one bond expands and the other compresses. Let us suppose we have the equilibrium position of carbon dioxide. Now, if this bond expands and the other bond compresses, it expands and it compresses. On the other hand, the bond on left hand side compresses and the bond on right hand side, bond on the left hand side expands and on right hand side it compresses. Now in this case, we have the polarizability ellipsoid for equilibrium position. As the polarizability of the bond which is expanding increases, but there is corresponding decrease in the polarizability of bond which is shortening or which is compressing, so the polarizability nearly remains the same. And we have the same polarizability ellipsoid. As in this vibration, the polarizability alpha does not change, hence it will be Raman inactive vibration. The vibration will be Raman inactive. Now we consider what happens to the dipole moment. As the bond, one of the two bonds elongates and the other shortens, that is why when we move in either directions, the dipole moment will increase. As the dipole moment or polarity of the molecule changes during this vibration, therefore this vibration will be IR active vibration. Here also the vibration is Raman inactive but IR active. Now we come to the third type of vibration, that is the bending vibration, in which the bond angle changes. Let us suppose we have this equilibrium position of carbon dioxide and it bends in plane of the in plane vibration, in plane bending vibration. In the equilibrium position, we have the polarizability ellipsoid, which is shown as below, as follows. Now, as we move towards bending. As the angle decreases, the polarizability decreases and polarizability ellipsoid increases. Now on both the sides, both extremes of vibration, the polarizability ellipsoid is repeated. So we have same polarizability on both the extreme ends. Therefore this molecule, this vibration, as the polarizability is unchanged, we can say that it is unchanged because it is repeated at two extremes. Therefore it will be Raman inactive. Now if we consider at the dipole moment, the linear molecule has a zero dipole moment, while the band structures have some values. Here we have also some value, and here we also have some value. As the dipole moment changes, therefore we say that it will be IR active. Same will be the case for bending vibration, which is out plane. Here also it will be Raman inactive but IR active. Now if we consider the four modes of vibration of carbon dioxide, they are either Raman active IR inactive, or they are Raman inactive IR active, and it indicates that carbon dioxide is a centrosymmetric. It has a center of symmetry. Here we have, here is the center of symmetry, and there is equal distribution of atoms. Therefore carbon dioxide is centrosymmetric. Now we can come to the second example, that is of water, and consider what are the different modes of vibration and what is their Raman activity and IR activity. Second example is water. We had already calculated that the total degrees of freedom in this case are 3n. There are 3 atoms in water. In this case we also have 3n, or 3 into 3 degrees of freedom, or 9 degrees of freedom. Out of these, translational degrees of freedom are 3. For non-linear molecules, rotational degrees of freedom are also 3. So the remaining degrees of freedom are the vibrational degrees of